Hello everyone, welcome to the channel. In this video we will be talking about lift generation. We will see how the lift is generated on the wing. We will be talking about pressure systems. We will be discussing Bernoulli principles, the Venturi effect, and we will see how the Venturi effect is helping us to generate lift on top of an airfoil. So let's get started. We need to first understand pressure systems first. So we have a formula which states total pressure is equals to static pressure plus dynamic pressure. These two terminologies are very important in terms of ATPL theory. We will be studying them in principles of flight. We will be studying them in aircraft journal knowledge and in instrumentation lessons. So let's see what static pressure is. Let's assume we have an object. So the pressure which is acting on an object from all the directions is known as static pressure. The object is stagnant, it is static, and the pressure which it is feeling is known as static pressure. Whereas in dynamic pressure, the object or the fluid has to move. We have an object, it is moving, and as we're talking about aviation, so we should use air mass as a reference. So we know that we have an air mass as a fluid, and this object is moving through this air mass. Now we know that these air particles will strike the object, and because of that some amount of pressure will be felt on the object, and that pressure is known as dynamic pressure. So if we add static pressure and dynamic pressure, we will get total pressure. So now we have some basic understanding about the pressure systems. Let's talk about what Bernoulli is telling us. So the Bernoulli principle says that whenever the velocity increases, the pressure will decrease simultaneously. To understand this much more clearly, let's take an example of what we call the throat effect or the Venturi effect. In Venturi effect, we basically take a tube with convergence in between. So as we can see, it is a tube which has slight converging area in the mid part, and the cross-sectional area over here in the mid is much more less than the cross-sectional area on the openings. Now what happens is, when the relative airflow or an air mass is passed through this tube, the airflow converges at the throat. Over here, because of the convergence, because of the design characteristic of this tube, the velocity will increase and the pressure will decrease, which means we have low pressure area. Now let's see how this example can help us generate lift. So we have an airfoil, and we can see it is a positively cambered wing. We can see that we have much more curvature on top of the wing than at the bottom of the wing. This curvature of the wing is known as camber. So we can see that the upper camber is much more than the lower camber. So we need this upper camber to be more in order to generate the same effect which was generated in the tube example which I showed you. So now we know that the upper curve of the wing is greater than the lower curve of the wing. We have more curvature on top of the wing as compared to the curvature on the lower side of the wing. So this airfoil design is giving us the same outputs and same results as we were getting from the Bernoulli example. We can repeat it once again. We said that if we have a tube with a smaller cross-sectional area in between and we pass the air mass through it, the velocity at the throat will increase and the pressure will decrease. So if we carefully observe this area of the throat, we can link it with the camber of the wing. We can directly see the same design characteristics on top of the wing. So the upper camber is providing us with the throat effect. Which means when the air mass or relative airflow or undisturbed airflow is striking the wing, and when it passes over the wing, the velocity of the air mass increases, the pressure decreases, and when we have reduction in pressure, we know there is some level of suction generated or vacuum generation takes place. Thus there is an upward force which is known as lift. We can also say that on top of the wing the dynamic pressure is higher and static pressure is low, whereas at the bottom of the wing the dynamic pressure is relatively lower and the static pressure is higher. And because of the difference in pressure, lift is generated.